Hi, this is JB Morin. I'm going to present you the speed acceleration, the sprint acceleration speed profile, and the idea of testing players without testing them. So this is a collaboration that we are now undertaking with people at GPXA in Italy, and I have no conflict of interest with the activities of this company, except for scientific collaboration, good times, and friendship. So basically, I'm going to summarize the classical use of the sprint force, velocity, and power profile. Everything comes from the idea of a macroscopic approach where we see the big picture first. And this is something that was mentored to us by Professor Di Prompero and explained in biomechanics by people like Robert Alexander, where they say that basically when you address something that's complex, such as sprinting and running performance, the simpler the model, the clearer it is which of the feature is essential to the calculated effect. And in our case, this is performance. So in the past, we have used the force velocity profile both in theoretical studies and practical applications. And basically, to summarize, this profile, as we will see in a few slides, is based on the increase in speed, running speed, that we fit and model and use to calculate the horizontal force output. So only the output of force that's used to move the center of mass as a function of velocity. And we derive an estimate of power associated to that force. So this was used in football. As you can see here, it was used in rugby in some of our studies. Some studies also recently published the use of that profile in ice hockey, in acceleration. And so basically, you can use that approach to assess the player's physical capabilities, to assess the rehabilitation process, to monitor the change in fitness in sprint mechanical outputs over time, the effects of training, the effect of fatigue, and maybe use that in prevention, as we will see after. So if you want to know more and access the papers and the blog posts, all that stuff, you can go to my website and visit some of the things we did in the past. So the typical example here is two players with the same 30-meter time, so the same performance overall, but their underlying mechanical outputs are really very different. And so it means that if you want to dig deeper into the reasons that explain performance from a biomechanical perspective, force velocity is useful to distinguish between athletes, how they orient the force, how they produce the force, at what velocity, etc., etc. So the reference methods to compute the profile, you can use sprint instrumented treadmills. This is very useful, but there's only two in the word. And you can also use force plates, which is the reference device, but there's only a few labs in the world where you can do that. So this is very frustrating, and this is why we thought about using a simple field method and some observations made almost 1 century ago by Archibald Hill in sprinting, and that have been consistently observed again and again, show that when people accelerate and when humans run at their maximum capability, their speed increases in a very simple exponential way. So this has been observed systematically, and it's very, very old observation. Different devices over the years. This is a study in Russia in the 70s, and same observation again. So basically, this is what Pierre Samozino published in 2016. If you know that increase in speed that's exponential, and it's something you see in sprinters, it's something you see in football players, in the world record of Usain Bolt. My son, for example, when he was a little kid, this old sprinter, when everybody accelerates, the increase in speed is clearly exponential. So from that, you can calculate the acceleration by deriving velocity over time, and you can estimate the ground reaction force that was associated with this acceleration. So to validate that method, we used force plates to compare, first in 2016 and second in 2019, where we replicated that validation study on the force plate system of Ryu Nagahara in Japan. And to summarize, we observed a very good validity and reliability of the method. You can see here the comparison between the estimated force with the equations and the actual force plate data. So it's reliable. You just need body mass, running speed, or split times. And in practice, you can use a camera to measure split times, timing gates, radar device. You can use the spreadsheet that we've developed to do the measurements, or you can also use GPS devices. And this is something that's been published today by Mathieu Lacombe and his team. If the GPS is accurate enough, then you can calculate the speed, fit with the exponential function, and calculate the force velocity profile. So this is good. And there are some applications, so I won't go into details because it's not the aim of the presentation, but we have applied this in many training contexts to answer the question, what type of training input can we use to improve what component of the force velocity spectrum? If I want to improve my maximum force, what should I do? If I want to improve other types of items or features of the profile, such as the ratio of force, the orientation, what should I use? We have been doing some research also on the injury side. How can we use the profile to help the hamstring injury management, for example? First, you can monitor the players and monitor the change in the profile, and maybe you can use that to help better design the training content and manage the training content. For example, as colleagues in this paper, very interesting paper, say, you can monitor the players to quantify their force and velocity capability so that the workloads are adjusted. For example, if a player has a very high V0, very high maximum velocity of running, maybe they can save some maximum speed sessions to focus on something else. Okay, so a bit of orientation of the training content. Now, if the player gets injured, the return to sport or the return to performance process can also benefit from using the force velocity profile. In this study by Jordan Mendiguchia, we saw that after return to sport, after rehabilitation, the players were tested in sprinting and their maximum power and maximum force output were still very low compared to the uninjured players. However, their maximum velocity was not. And 2 months after, the entire values were back to normal. So it means that in their force velocity profile, there was something that was not ready to return to play and something that was functionally sprint related and that was not okay. We observed that again in a field monitoring study, in a case study where the player post-injury had a very low force output compared to pre-again. So this is a typical example of that kind of use. In that player, professional rugby player, who had a hamstring injury here, we used the pre-injury profile as a target for the post-injury rehabilitation. So basically, until the player was not tested as back to normal, he kept on doing some rehabilitation until the force velocity profile was equal or better than before. All right, time to play and time for some specific team sport approach. So this is the in-situ profile. It's an idea we had based on trying to mix lab and field testing, which is one of our main topic of research. So all models are wrong. So the force velocity model is wrong in the sense of not perfect, but some are useful. And we think that the force velocity approach is useful. However, one of the main limitations is that you need to do a test. And as you know, a test is a stress for football players and for team sport players and all types of athletes. So the idea was, can we get the same type of information without testing the players? So the idea of the in-situ profile is to get all the GPS data of speed and acceleration. So every movement, 20 times per second, you have a speed and acceleration point. So this here, the cloud here in red, is the equivalent of 2 weeks, 8 sessions for a pro football player. And so we have all the data here. And what you see is that for each speed through the spectrum, he was able to produce some accelerations that were low, intermediate, or very high. And we select for analysis only the two highest acceleration values for each 0.2 meters per second increment starting at 3 meters per second, because before 3 meters per second the acceleration is never maximum. So you have a spectrum that goes from about the max acceleration to the max speed, and you extrapolate that spectrum to plot a linear regression on the points I just described. So it's about 40 to 60 points on average. And this is the extrapolation line that you get, and this line is actually the acceleration speed profile in football, and this describes the limits of the physical capabilities of that individual player in the very specific situation of football. And you can extrapolate the values and compute two more variables, A0, which is the theoretical maximum acceleration of the profile, and S0, which is the theoretical maximum speed. So A0 and S0 describe that player capability over that 2 weeks period. Here, for example, the same player did a classic 30-meter test, and this is the black data, the black dots that you have here. This is a 30-meter test GPS data. And you can see here that this is the acceleration speed profile of his specific test. So be very careful. This is not the same type of information. One is a single test, the other one is not a test. It's 2 weeks of data that were pooled and analyzed. Here, another example. This is one professional player, 7 full sessions of football. One was a single sprint test. Here is the cloud of data of the 7 sessions, and boom, if you pool that cloud of data, you have the 2-week in-situ profile. So our experience right now is to use 2 weeks of data, because you need at least 6-7 sessions of football to get a good amount of data to do a strong linear relationship. So that's the individual player's maximum sprint spectrum. So the idea basically came to us by reading a study in cycling by Pinot and Grapp, the power record profile in cycling, where instead of doing several tests or a single test on a very long distance and a very long time, they take the power data of the cyclist over several training sessions, maybe some races, etc., etc. And when you get enough data, you can build the power-time relationship for that cyclist, and you see that it's very different between cyclists. And this is the powered record profile. You never tested the cyclist. You just took their power values and reanalyzed them. So if you want to compare the classic force velocity profile with the new in-situ acceleration speed profile, you should remember that it's similar but different information. First, one is a single test, it is linear sprinting, and it is only semi-specific to football, okay? It is sprinting, but it's not football. The other one is football data, minimum of 6 sessions, so it's not a single test. It includes all types of acceleration and movements, and it is very football specific. You cannot do a more specific. You can even include some game data. So here, I would just like to plot on the same graph the force velocity and the acceleration velocity profile. And you see that the only difference is the air friction, but on the y-intercept, because there's no air friction, F0 and A0 expressed in different units. F0 is in newtons per kilo and A0 is in meters per second square. They are conceptually exactly the same quantity. And here you have the maximum speed. So be very careful. You don't want to take one information as an expression of the other. You just count what counts for you. If you want to do a linear test to know some specifics, do it. If you want to look at the football specific data, do it. But don't mix the information. So the study we are doing now is a preliminary study on 16 professional players. It's a proof of concept study, and basically the first result is that the linear profile has been observed clearly on all the in-situ data. The R-squared are really very high, but you need at least 6 sessions to build a strong relationship on at least 40 to 50 points. We observed very low inter-period variability, so that's where we compare 2 week to another 2 week just after. So classical statistics are very good here. And this is an example of a player 2 weeks pre-test, 2 weeks post-test. Of course, it's not the same 2 weeks of football. Maybe the sessions are different. It's not the same player physically, but overall the data are pretty close. So there are similarities and there are differences with the test FV profile. So to summarize one of the differences, we observed that the maximum acceleration is higher in football than in a linear sprint test, but on the opposite, the maximum speed is higher on the sprint test than during football sessions. So this is the research I like. You answer one question and you open 20 questions. First, is that in-situ profile reliable? The answer is yes, and we are going to publish that. How does it change with fatigue? Is it influenced with session fatigue, training cycle fatigue? Is it influenced by small-sided games, the type of games, seasonal changes? How does it change over the season? Is it different between players for each position? Is it influenced by tactical periodization? For example, if the coach says, I think that this session puts an emphasis on the acceleration, then you can verify that with the profiles. Is it influenced by the playing style of the team? Training blocks, you want to improve, I don't know, maximum speed in players. Does the training block build some maximum speeds? Does the profile change after injury? Does it change maybe before injury? That's a lot of questions that maybe not us, but people will answer in the future. But for now, we only started with presenting that method we've been thinking about. So I want to thank the entire team. This is the team that's working on the project. So myself, Pietro Di Prampero, Christian Osnash, and Pierre Samozino and Jan Lemat. So thank you all, and very soon some news and likely some publications. So injury. So basically you can use the force velocity profile to help better decide when is the player ready to perform. Using a colleague